There is a kind of stillness that exists only at night, when the world above has quieted and the air itself seems to settle into something heavier, something patient. In that stillness, if you listen carefully enough, you begin to sense what lies beneath, not through sound, but through the sheer weight of presence. The way ancient stone presses upward against the thin skin of soil and cities and restless human time. Somewhere far below, older than language, older than light as we know it, there are structures that have simply refused to yield, that have remained exactly where they formed when the planet was still learning what it meant to be solid. And tonight, in this quiet hour, we descend toward them, not to disturb, but to acknowledge that they are there, holding everything we know on their shoulders. If this kind of slow reflection feels like the right place to rest your thoughts, you're welcome to subscribe to Quiet Science and continue these journeys into the silent depths with us, where science and stillness meet without hurry. We are going to spend time tonight with things that do not change quickly, with stone that remembers a version of Earth we could never witness, with formations so enduring that our entire human story could repeat 1,000 times over, and they would barely notice, still resting in the same darkness, still carrying the same memory in their crystalline structure. The planet has a way of preserving certain things, not out of sentimentality, but out of sheer physical inevitability. Some materials, some arrangements of atoms, are simply too stable to be undone, too deep to be reached by the processes that remake everything else. And so they remain, quiet witnesses to billions of years, asking nothing, explaining nothing, simply existing in a patience we can barely comprehend. And perhaps that is exactly what makes them worth contemplating as the night deepens around us. To understand what it means for something to still exist inside the Earth after billions of years, we first have to reckon with the fact that almost nothing survives that long. Not in any form we would recognize, not in any place we could reach or touch or even imagine visiting. The surface of this planet is a place of relentless revision, where mountains rise only to be worn smooth by wind and rain, where entire ocean floors are dragged beneath continents and melted back into formless magma, where even the hardest granite eventually crumbles into sand and is carried away by rivers that themselves will one day cease to flow. Everything exposed to air and water and the patient work of chemistry is subject to change, subject to being unmade and remade into something else entirely. And this has been happening continuously, without pause, for as long as the Earth has had a surface cool enough to hold liquid water. But depth changes everything. The deeper you go, the more protected materials become from the surface's restless remaking. The more removed they are from the cycles of erosion and weathering and biological interference that dominate the thin outer shell where we live our lives. At a certain point, deep enough down, the conditions stabilize in ways that allow stone to simply remain, held in place by its own immense weight, pressed between layers of other ancient stone, protected by darkness and pressure, and the sheer distance from anything that might disturb it. The Earth is not a static sphere of rock, but a dynamic engine of transformation, its interior constantly churning in slow motion as heat from the planet's formation and from the decay of radioactive elements drives massive currents through the mantle, the thick layer of hot but solid rock that lies between the crust we walk on and the molten iron core far below. These currents, moving at speeds measured in centimeters per year, carry material in great looping cycles that can take hundreds of millions of years to complete, dragging oceanic crust down into subduction zones, melting continental margins, pushing continents across the surface like slow-motion ships adrift on a viscous sea. And yet, within all this motion, there are pockets of profound stability, regions where the rock has somehow avoided being caught up in these cycles, where material from the planet's earliest days has remained chemically isolated, physically undisturbed, locked away in configurations that formed when Earth was an entirely different world. It is not that these structures are indestructible, but rather that they exist in places and under conditions where nothing has come along with sufficient force to destroy them, and time alone, without the application of heat or pressure or chemical intrusion, is surprisingly gentle. A crystal, once formed, can sit for 1 billion years in perfect darkness and remain exactly as it was the moment its atoms locked into their repeating lattice. Because at the atomic scale, in the absence of energy to break those bonds, there is no mechanism for change. The stone simply rests, neither growing nor shrinking, neither warming nor cooling beyond the background temperature of its surroundings, waiting in a patience so complete it cannot even be called waiting, because waiting implies expectation, and these structures expect nothing. When we speak of the oldest materials inside the Earth, we are speaking primarily about two kinds of survival: minerals that formed early and managed never to be melted again, and larger-scale structures, entire domains of mantle rock or fragments of ancient crust that have resisted being pulled into the planet's convective churning. Both represent extraordinary endurance, but of different kinds. A single crystal the size of a grain of sand can be older than entire mountain ranges, can predate complex life by billions of years, simply because it happened to form in a durable mineral species, and then spent its existence embedded in rock that was never subjected to temperatures high enough to dissolve it back into magma. Meanwhile, vast sections of the deep mantle, thousands of kilometers across, have remained chemically distinct from their surroundings, not because they are harder or stronger, but because they settled into a density equilibrium that left them undisturbed by the convective flows moving past them, like boulders in a slow river that the current simply cannot dislodge. Neither is trying to survive. Neither possesses any quality we might call resilience in the biological sense. They persist simply because the specific combination of their composition, their location, and the physical conditions around them has never aligned in a way that would require their destruction. And in the deep earth, where processes unfold across timescales so vast they make human history look like a single heartbeat, that passive resistance to change is enough. What we are really contemplating then is not strength but circumstance, not immortality, but the simple absence of forces sufficient to cause dissolution. The oldest structures inside the Earth are not ancient because they fought to remain, but because they were, by geological accident, placed beyond the reach of the mechanisms that recycle everything else, and there, in that deep protection, they have remained, neither aware of their own age nor diminished by it, holding within their atomic arrangements a record of conditions and processes that no longer exist anywhere else in the solar system, a kind of memory written not in neurons or symbols, but in the precise spacing of atoms, in isotopic ratios that tell of a time when the planet's surface was molten, when the atmosphere was poison, when the moon hung closer in the sky and the days were only a few hours long. And perhaps what is most remarkable is not that these structures are old, but that we, so recently arrived, so briefly present, have found ways to read that memory, to extract from silent stone the story of a world we will never see, and in doing so, to place ourselves, however humbly, in continuity with a history that preceded us by an almost incomprehensible margin. The smallest survivors are, in many ways, the most remarkable because they have persisted not through isolation in some protected deep chamber, but through sheer molecular stubbornness, tumbling through the full violence of geological recycling and emerging intact on the other side, over and over again, for time spans that dwarf the existence of recognizable continents. Zircon crystals, no larger than grains of sand, some no bigger than a speck of dust caught in slanting light, represent the oldest tangible pieces of Earth's early history, fragments that formed when the planet was still in its infancy, and have somehow remained coherent ever since, passing through environments that should have destroyed them but didn't, not quite, because the particular arrangement of zirconium, silicon, and oxygen atoms that defines their structure happens to be among the most chemically stable configurations known to occur naturally. They form in molten rock as it cools, crystallizing out of magma in the final stages of solidification, and once formed, they resist being dissolved back into liquid even when the surrounding rock melts again, even when temperatures climb high enough to turn granite into flowing glass. Because zircon's melting point is higher, its bonds tighter, its reluctance to disassemble nearly absolute. This means that while the rock around them is churned and melted and reformed countless times, the zircon grains simply pass through, like pebbles rolling through a river that cannot wear them smooth, accumulating the journey in their structure, but never losing their essential form. The oldest of these crystals, found embedded in much younger sandstone in a remote region of Western Australia, have been dated to over 4 billion years ago, which places their formation within the planet's first 500 million years of existence, a time when Earth was barely recognizable as the world we know now. The surface was likely still partially molten in places, the atmosphere thick with volcanic gases, the moon looming larger and closer in the sky, and yet somehow, in the midst of that primordial chaos, these tiny crystals formed and hardened and began their long journey through time. What makes them scientifically invaluable is not just their age, but what they contain within their atomic lattices. Because when a zircon crystallizes, it incorporates small amounts of uranium into its structure while excluding lead, and uranium decays into lead at a rate so consistent it can be used as a clock, allowing scientists to measure with extraordinary precision exactly when the crystal formed. But more than just telling us their own age, these ancient zircons carry chemical signatures that reveal something profound about the environment in which they crystallized. Ratios of oxygen isotopes that suggest the presence of liquid water at the surface far earlier than previously thought, implying that Earth cooled quickly enough after its formation to have oceans within its first few 100 million years, transforming our understanding of how rapidly the planet became habitable, or, at least capable of harboring the conditions from which life would eventually emerge. What strikes me most about these crystals is not just that they are old, but that they are so small, so unremarkable in appearance, so easily overlooked if you did not know what you were looking at, and yet they contain within their microscopic structure a witness record of a world that no longer exists, a version of Earth that predates plate tectonics as we know it, that predates the oxygenation of the atmosphere, that predates every living thing, every mountain range, every ocean basin, everything we would recognize as terrestrial geography. They are not fossils because they were never alive, but they are witnesses nonetheless, silent observers that have seen the planet transform around them while they remained chemically unchanged, passed from one generation of rock to the next, like heirlooms, eroded out of ancient mountains, washed into rivers, deposited in sediments that later hardened into sandstone, and then, millions of years later, eroded out again, recycled endlessly through the surface processes that grind continents down and build them back up. And through it all, the zircon itself remains, its internal clock still ticking, its isotopic ratios still recording the precise moment of its formation, waiting in perfect patience for someone to find it and read its message. The fact that we can hold one of these crystals, if we are careful enough and fortunate enough to be given access to such precious samples, and know that we are touching something that formed when Earth itself was young, something that existed before the first known rocks, before the first stable continents, is both humbling and oddly comforting, because it places us in direct physical contact with deep time, not as an abstract concept, but as a tangible reality that can rest in your palm, invisible to the naked eye perhaps, but undeniably real, undeniably ancient, undeniably connected to a past so remote that our minds struggle to construct any meaningful analogy for its distance from the present. And yet the zircon does not care about this profundity. It does not know it is ancient. It simply exists as it has existed, with the same molecular patience it has always possessed, neither proud of its survival nor aware of it, holding its secrets not deliberately but inevitably, because that is what its structure does. That is what stability at the atomic level means. And perhaps there is something to be learned from that kind of existence, that kind of presence without intention, that ability to simply remain century after century, eon after eon, unchanged and unchanging, while everything around it rises and falls and is forgotten. While zircon crystals represent survival at the scale of individual grains, there are structures of a different magnitude entirely that have persisted through comparable spans of time, not by being hard enough to resist destruction, but by being too large, too stable, too deeply rooted to be easily moved or broken apart by the forces that constantly reshape the Earth's surface. These are the cratons, the ancient cores of continents, vast platforms of thick, cold, stable rock that form the foundation upon which younger geological features are built, and they have remained essentially intact, in some cases, for over 3 billion years, which means they were already ancient when the first complex cells appeared. Already old when the atmosphere first accumulated significant oxygen, already stable and enduring while the planet's surface was still being assembled into something resembling its modern configuration. They are not indestructible, but they are profoundly resistant to the processes that consume and recycle most crustal material, and their persistence tells us something fundamental about how the Earth organizes itself, how certain configurations of rock, once established, can achieve a kind of gravitational equilibrium that makes them nearly impossible to disrupt. The key to a craton's longevity lies in its thickness and its temperature, two qualities that work together to create stability in ways that might seem counterintuitive at first, because we tend to think of thickness as making something more vulnerable to bending or breaking under stress. But at the scale of tectonic plates, thickness combined with coldness creates buoyancy and rigidity that protects rather than endangers. A craton consists not just of the continental crust we can see at the surface, but of a deep root of lithosphere extending down into the mantle, sometimes reaching depths of 200 kilometers or more, far deeper than the oceanic lithosphere that surrounds it. And this root is cold, much colder than the surrounding mantle rock at equivalent depths, which means it is denser in some ways, but also more viscous, more resistant to flowing, more difficult to pull down into the convective currents that drive plate tectonics. When oceanic crust collides with continental crust at a subduction zone, it is always the oceanic plate that bends and descends, always the thinner, younger, hotter plate that gives way, because the old, cold, thick continental root simply cannot be forced downward, cannot be made to sink into the mantle, no matter how much force is applied from the sides. The craton remains at the surface, unmoved, while everything around it is recycled into the deep earth. These ancient continental cores can be found at the heart of every major continent, forming the stable interior regions that geologists call shields when they are exposed at the surface, or platforms when they are buried under younger sedimentary layers, and they share certain characteristics wherever they occur, a family resemblance that speaks to their common origin in the planet's distant past. The Canadian Shield, the Australian Shield, the African cratons, the Siberian platform, each represents a fragment of very old Earth, assembled during a time when the planet's heat engine ran hotter and the dynamics of crust formation were different from what we observe today. They are composed largely of granite and metamorphic rocks that have been so thoroughly processed by heat and pressure that their original character is difficult to determine. But isotopic analysis reveals formation ages that cluster in certain periods, particularly between 2.5 and 3.5 billion years ago, a window of time when the Earth seems to have been especially productive in creating large volumes of stable continental material, though the reasons for this remain debated, part of the larger puzzle of how and when the modern style of plate tectonics began. What makes these cratons remarkable is not just their age but their coherence, the fact that they have held together as recognizable units through billions of years of tectonic shuffling, surviving the assembly and breakup of multiple supercontinents, remaining intact while the plates around them collided and fragmented, and were subducted and replaced. And this coherence suggests that once a craton forms, once it reaches that critical combination of thickness and coldness and chemical composition, it becomes nearly permanent, or as permanent as anything can be on a dynamic planet. The forces that tear younger continents apart, that create rift valleys and eventually split landmasses into separate pieces, often fail when they encounter cratonic rock, the rifts simply dying out as they reach the old, cold, thick lithosphere that refuses to be pulled apart. The margins of cratons can be deformed, buckled, thickened by continental collisions, but the core itself remains largely unaffected, sitting quiet and stable beneath whatever mountain ranges or sedimentary basins happen to form on its surface, outlasting them all, because mountains are temporary and sediments are temporary, but the cratonic root, once established, endures. There is something almost restful about this stability, about the idea that beneath the changeable surface, beneath the cycles of erosion and deposition and tectonic collision that create the landscapes we inhabit, there exists this foundation of ancient rock that has simply been there, holding its place, neither expanding nor contracting in any significant way, for a duration so vast it makes human civilization look like a brief flicker. We build our cities on these stable platforms without knowing it, farm the soils that have accumulated on their surfaces, draw water from aquifers trapped in their sedimentary cover, and all the while, kilometers below, the old cold route remains exactly where it has been since long before anything we would recognize as familiar existed on this planet. And it will remain there, in all likelihood, long after we are gone, continuing its patient existence, neither marking time nor being marked by it, simply present in a way that requires no effort and no awareness, a foundation so deep and so stable that it might as well be eternal, even though nothing truly is. If we continue descending, moving past the continental roots and the mobile upper mantle, where most of the Earth's convective churning takes place, we eventually reach a boundary at a depth of about 660 kilometers below the surface, where the crystal structure of the dominant mantle minerals changes in response to the immense pressure, rearranging into denser, more compact forms. And this transition marks the beginning of the lower mantle, a vast region that extends all the way down to the core mantle boundary, nearly 2,000 kilometers deeper still, comprising more than half of the planet's total volume. And it is here, in this deep realm of extreme pressure and ancient stillness, that some of the oldest and most chemically pristine materials inside the Earth have been quietly resting, largely undisturbed, since very early in the planet's history. The lower mantle is not static in any absolute sense, because no part of Earth's interior is truly motionless, but it moves far more slowly than the upper mantle, its convective currents broader and more sluggish, taking hundreds of millions of years to complete a single circulation. And within this general slow motion, there are regions that appear to have been essentially isolated from mixing for billions of years. Pockets of rock that retain the chemical signature of the primitive mantle, the original material from which the Earth accreted before any differentiation into crust and core had occurred. Preserved not by being locked in some impenetrable vault, but simply by occupying zones where the convective flows happen to circulate around them rather than through them. The pressure at these depths is almost beyond comprehension, measured in millions of times the atmospheric pressure we experience at sea level, enough to compress rock into structures that bear little resemblance to the minerals we find at the surface, transforming familiar compounds into exotic high-pressure phases, with names like bridgmanite and post-perovskite, materials that can only exist under these extreme conditions, and would instantly transform into something else if brought to shallower depths. Under such pressure, even solid rock behaves differently, flowing like an extraordinarily viscous fluid over geological timescales, deforming and rearranging itself in response to stress, but doing so slowly enough that we can still meaningfully speak of structures persisting, of regions maintaining their identity, because the rate of mixing and homogenization, while never zero, is slow enough that chemical heterogeneities established billions of years ago have not yet been erased. It is as though the lower mantle exists in a state of suspended transformation, changing so gradually that from any human perspective it might as well be eternal. And yet from the planet's perspective, it is continuously, if imperceptibly, evolving, flowing, rearranging itself in patterns so vast and so slow, they dwarf even the long cycles of continental drift that reshape the surface. What allows certain regions of the lower mantle to remain chemically distinct is a combination of their composition and their position in the convective system. Because the mantle does not mix uniformly the way water in a pot might mix when heated from below, but rather organizes itself into complex three-dimensional patterns of upwelling and downwelling, with material rising in some places and sinking in others. And between these flows, there are relatively quiet zones where the rock simply sits, compressed by the weight of everything above it, heated by the slow decay of radioactive elements within it, but otherwise undisturbed by the large-scale movements happening elsewhere. These quiet zones can be detected by studying how seismic waves travel through the Earth, because waves move at different speeds through materials of different composition and temperature, and careful analysis of earthquake data from stations around the world has revealed the existence of large low-shear velocity provinces deep in the lower mantle beneath Africa and the Pacific, vast blob-like structures thousands of kilometers across, where the rock appears to be chemically different from the surrounding mantle, possibly representing material that has remained separate since the planet's formation, or perhaps the accumulated remains of ancient oceanic crust that was subducted long ago and has settled at the base of the mantle without fully mixing in. The existence of these primitive reservoirs, if that is indeed what they are, tells us something profound about the planet's thermal and chemical evolution, because it means that Earth has not fully homogenized despite billions of years of convective stirring, that there are still regions that preserve a record of its earliest composition, islands of memory in a sea of slow transformation. The mantle, in this view, is not a uniform ball of rock that has been thoroughly mixed and remixed countless times, but rather a layered and heterogeneous body with a complex internal architecture, containing within itself multiple generations of material, some ancient and primitive, some relatively young and derived from recycled crust, all coexisting in the same physical space, but maintaining their chemical identities through the simple fact that mixing at these depths and pressures and temperatures is not complete, not efficient enough to erase every distinction, not fast enough to prevent isolated pockets from persisting for timescales measured in the billions of years. And this incomplete mixing is not a failure of the system, but a feature of it, a natural consequence of the physics governing viscous flow in a body of this size and composition, where stirring occurs but slowly, where gradients flatten but not entirely, where the past continues to coexist with the present in ways that would be impossible in a smaller, faster system. To imagine this kind of persistence requires a recalibration of our intuitions about change and permanence, because we are accustomed to thinking of liquids as things that mix quickly and solids as things that stay put. But the lower mantle is neither quite liquid nor quite solid by any definition we would apply at the surface, and its behavior over geological time follows rules that seem almost contradictory, simultaneously flowing and holding its structure, simultaneously dynamic and stable, ancient beyond measure and yet never quite finished transforming. The stone at these depths has no way of knowing its own age, no mechanism for recording time passing, and yet it carries within its chemical composition a date stamp that speaks of the planet's earliest days, a ratio of isotopes that reveals when it first formed, and that information remains readable billions of years later because the atoms themselves have not been significantly redistributed, have not been melted and rehomogenized into the general mantle population, but have instead simply remained where they settled, compressed into stillness by the weight of half a planet pressing down from above. There is another kind of ancient material residing in the deep earth, not primitive rock that has remained undisturbed since the planet's formation, but rather something that was once young and recently created at mid-ocean ridges, fresh basalt cooling from magma that welled up from the mantle to form new seafloor, and which then spent millions of years traveling slowly across the ocean basin, accumulating sediment on its surface, growing colder and denser with age, until eventually it reached a subduction zone and began its long descent back into the interior from which it originally came, pulled down by its own weight into the mantle's depths, where it was compressed and heated and transformed into something denser and harder, but never quite fully dissolved back into the surrounding rock. And these slabs of ancient oceanic crust, some of them subducted hundreds of millions of years ago, possibly even billions in some cases, now rest at various depths throughout the mantle, recognizable in seismic images as regions where waves travel slightly faster than they do through normal mantle rock, marking the presence of material that is colder or compositionally distinct or both, a graveyard of former ocean floors stacked and folded in the planet's interior. When oceanic crust first forms at a spreading ridge, it is hot and buoyant, riding high on the underlying mantle because it has just been extracted from depths where temperatures are high enough to melt rock. But as it moves away from the ridge and ages, cooling from the surface downward, it becomes progressively denser, and the lithosphere beneath it, the rigid plate that includes both the crust and a layer of uppermost mantle frozen onto its base, grows thicker and colder and heavier with time. After a few tens of millions of years, the plate becomes dense enough that when it encounters a continent or another oceanic plate at a convergent boundary, it will begin to sink, bending downward into the mantle in a process that, once started, becomes self-reinforcing because the deeper the slab descends, the more it is heated and compressed. And while heating should make it less dense, compression wins out at these pressures, transforming the minerals in the slab into denser high-pressure forms that pull it downward with increasing force, a gravitational anchor that drags the entire plate behind it, driving the motion of subduction and, by extension, much of the surface tectonics we observe. The slab does not fall quickly because the mantle, despite being able to flow over geological time, is enormously viscous, resisting motion the way honey resists being stirred. But fall it does, sinking at rates of a few centimeters per year. And over millions of years, this accumulates into descents of hundreds or even thousands of kilometers. What happens to these slabs once they reach the deep mantle has been a subject of considerable scientific debate, because for a long time, it was unclear whether they penetrated all the way to the core mantle boundary or stalled at the 660-kilometer discontinuity where the lower mantle begins, piling up in a kind of slab graveyard at mid-mantle depths. Seismic imaging has now revealed that both outcomes can occur, that some slabs do indeed penetrate into the lower mantle and continue descending, while others flatten out and spread horizontally at the upper-lower mantle boundary, stalled by changes in viscosity or density that make further descent difficult, and the fate of any particular slab depends on its temperature, its composition, its age, and the details of the convective flow patterns in the mantle at the time and place of its descent. But regardless of whether they reach the core mantle boundary or stop partway down, these slabs represent material that was once part of the seafloor, that once felt the pressure of ocean water above it and the slow rain of sediment settling onto its surface, and which now rests in darkness and heat and pressure so extreme that its minerals have been entirely reorganized at the atomic level. Basalt transformed first into eclogite, and then into even denser assemblages that exist only at lower mantle pressures. And yet, despite this transformation, the slab retains a chemical identity distinct from the mantle through which it fell, because the process of melting that created the oceanic crust in the first place left it with a different ratio of elements, slightly enriched in some components, slightly depleted in others, and these chemical signatures persist even after the minerals themselves have changed. Some of the slabs currently residing in the deep mantle may have been subducted recently, geologically speaking, within the last 100 million years or so, and these are relatively easy to identify in seismic images because they are still significantly colder than their surroundings, but others have been down there much longer, long enough to have thermally equilibrated with the ambient mantle, and these are harder to detect, visible only through subtle differences in seismic velocity that might indicate compositional rather than thermal anomalies. There is evidence, though still debated, that some slabs may have been accumulating at the core mantle boundary for 1 billion years or more, slowly building up a layer of recycled crustal material at the base of the mantle, a kind of sediment at the bottom of the convecting system. And if this is true, then these represent some of the oldest coherent structures in the planet's interior, not in the sense of being made of primitive material, but in the sense of having maintained their structural and chemical identity for an immense span of time, despite existing in an environment where everything is theoretically capable of flowing and mixing given enough time. They are ancient, not because they are original, but because once they arrived at their resting place, they simply stopped moving in any significant way, settling into a configuration so stable that the passage of hundreds of millions of years has not substantially altered their position or composition. The ocean floor that is being subducted today, beneath the Pacific Ring of Fire, descending into the mantle at the Marianas Trench or off the coast of South America, will eventually join this archive of former surfaces, will be compressed and heated and transformed, and potentially, if it sinks far enough, will come to rest at the core mantle boundary, where it might remain for 1 billion years before being swept back up by some future convective upwelling and recycled into new magma and perhaps, eventually, new crust. The atoms in that basalt might have been part of a dozen different ocean floors before this one, cycled through the system repeatedly over the planet's history. But each time they descend, each time they are buried and preserved in the deep interior, they spend an interval measured in hundreds of millions of years simply waiting in the dark, neither moving significantly nor changing significantly. A pause in the endless circulation that is long enough to seem like permanence from any perspective that matters to creatures like us who live and die within a geological instant. At the very center of the planet, deeper than any of the structures we have considered so far, there exists something paradoxical, a sphere of solid iron roughly 1,200 kilometers in radius, compressed under pressures that exceed 3 million times atmospheric pressure at sea level, heated to temperatures comparable to the surface of the sun, and yet stable, crystalline, growing imperceptibly at its outer edge as more iron freezes onto it from the molten outer core that surrounds it. And this innermost sphere, this final destination of our conceptual descent, is in some ways the youngest of all the ancient structures inside the Earth, having formed not during the planet's early history, but much later, possibly as recently as 1 billion years ago, which means it did not exist when the first complex life appeared, was not yet solid when the first animals emerged in the oceans, came into being only after the Earth had already spent billions of years cooling from its initial formation. And yet, despite its relative youth compared to the primitive mantle or the oldest cratons, it represents perhaps the most complete form of stillness available anywhere in the planet's interior. A core within the core where motion has essentially ceased, where the iron atoms are locked into a crystalline lattice so stable that nothing short of the Earth's eventual death, billions of years from now, is likely to disturb it. The inner core exists because of a simple principle that governs how materials behave under extreme pressure. When you compress something hard enough, you can force it to solidify even at temperatures that would normally keep it molten, because pressure favors the denser, more organized state that we call solid over the less ordered liquid state. And at the conditions prevailing at the Earth's center, the pressure is sufficient to overcome the thermal energy that would otherwise keep the iron liquid, allowing it to crystallize despite being intensely hot. The outer core, which extends from about 3,000 kilometers depth down to about 5,000 kilometers, remains liquid because the pressure there, while immense by surface standards, is not quite enough to force solidification at the temperatures that prevail, and so the iron and nickel alloy that makes up the core flows in complex patterns driven by heat escaping from the inner core and by the planet's rotation, generating the magnetic field that shields the surface from solar radiation and makes compasses work, a dynamo of molten metal in constant turbulent motion. But at the very center, where the pressure reaches its maximum, the iron can no longer sustain the liquid state, and it freezes, not because it has cooled below some critical temperature, but because the pressure has climbed above the critical threshold where solid is thermodynamically favored over liquid. This inner core has been growing throughout its existence, fed by the gradual cooling of the Earth's interior, because as heat slowly leaks out of the planet into space, the outer core cools ever so slightly, and when liquid iron at the boundary between the outer and inner cores cools just enough, it crystallizes and adds itself to the solid inner core, releasing latent heat in the process, heat that helps drive the convection in the outer core and thus contributes to maintaining the magnetic field, creating a feedback loop where the growth of the inner core helps power the very magnetic field that has protected the surface environment throughout most of the planet's history. The rate of this growth is extraordinarily slow, measured in millimeters per year at most, possibly less. So slow that even over millions of years the inner core's radius increases by only a few kilometers. And yet this slow accumulation is inexorable, because the planet is cooling, must cool, will continue cooling until it reaches thermal equilibrium with space, a state billions of years in the future when the interior will finally be cold enough that convection ceases and the core solidifies entirely, and the magnetic field dies. But that end is so distant that for all practical purposes, the inner core's growth can be thought of as eternal, a process that began long ago and will continue long into the future, adding layer upon layer of crystallized iron in a patient accretion that asks nothing and expects nothing, and simply occurs as a consequence of basic thermodynamics. What makes the inner core remarkable as a structure is not just its composition or its extreme conditions, but its isolation, because it is surrounded by liquid metal that effectively decouples it from the rest of the planet, allowing it to rotate at a slightly different rate than the mantle and crust above, spinning independently like a planet within a planet, free to respond to gravitational and magnetic forces in ways that the solid outer layers cannot. And this independence means that the inner core has its own dynamics, its own subtle motions and adjustments. Though these occur on such long timescales and at such small amplitudes that calling them motion almost seems like an exaggeration, more like an infinitesimal wobble, a barely perceptible deviation from perfect stillness. The iron crystals that make up the inner core are aligned in patterns that seismic studies have revealed to be complex and not entirely understood, with different regions showing different crystallographic orientations, suggesting that the inner core has some kind of internal structure, perhaps related to how it has grown over time or to currents in the overlying outer core that influence the pattern of crystallization. But whatever the cause, the result is a body that, despite being younger than almost everything else we have discussed, feels more permanent than any of them, because it exists in a state so far removed from the conditions that govern change at the surface that it might as well be in a different universe. The inner core will never erode, will never be subducted, will never be melted or weathered or broken apart by any process currently active in the Earth system, because nothing can reach it, nothing can apply sufficient force to disturb it, and the conditions under which it exists are so stable that they will remain essentially unchanged until the planet's thermal engine finally runs out of energy billions of years from now. It is the ultimate foundation, the deepest anchor, the final solid reference point at the center of all the motion and transformation that characterizes the layers above it, and in its perfect isolation, it embodies a kind of permanence that even the oldest cratons cannot match, not because it is older, but because it is unreachable, untouchable, removed by depth and pressure and heat from any mechanism of change, existing in a darkness so complete that light has never reached it and never will, resting in a stillness so profound that it makes even geological time feel rushed by comparison. If we could somehow descend into the inner core itself, past the boundary where liquid becomes solid and into the heart of the crystalline sphere, we would encounter not chaos, but an almost perfect order, because iron under these extreme pressures does not freeze into a random jumble of atoms, but rather organizes itself into precise geometric patterns, crystal lattices, where each atom occupies an exact position relative to its neighbors, repeated billions upon billions of times throughout the sphere, creating a regularity and symmetry that extends across hundreds of kilometers in every direction. And this crystalline structure is not merely an aesthetic arrangement, but a necessity, the only stable configuration available to iron atoms when they are compressed by the weight of an entire planet and heated to temperatures where the atoms vibrate intensely but cannot escape their assigned positions. The crystal lattice that iron adopts at these conditions is thought to be hexagonal close-packed, a structure where each iron atom is surrounded by 12 nearest neighbors, arranged in a pattern that maximizes density, squeezing the most matter into the least space. And this configuration is held in place not by chemical bonds in the traditional sense, but by the sheer mechanical pressure of everything above pressing down, a compression so intense that the atoms have no room to move, no possibility of rearranging themselves into any other pattern, locked into their positions with a force that makes the strongest materials at the surface seem fragile by comparison. What this means at the atomic scale is that each iron atom sits in a tiny cage defined by its neighbors, and though the atom vibrates with thermal energy, oscillating around its equilibrium position at frequencies so high they blur into a continuous tremor, it cannot leave that position, cannot migrate to a different site in the lattice, cannot do anything except vibrate in place. And this imprisonment by pressure creates a kind of stability that is absolute, because unlike chemical bonds which can be broken by sufficient energy, the mechanical constraint imposed by 3 million atmospheres of pressure simply cannot be overcome by thermal motion, not at temperatures anywhere near what exists in the core, not without adding energy from some external source that does not exist down here in this isolated sphere at the planet's center. The atoms are not trying to remain in place, because atoms do not try anything. They simply respond to the forces acting on them, and in this case, the forces dictate perfect immobility, perfect repetition, a crystalline order maintained not through any inherent stability of the structure itself, but through the external constraint of pressure too great to resist. And the result is a solid that will remain solid, a crystal that will remain crystalline, for as long as these conditions persist, which is to say, for the remainder of the planet's existence as a geologically active body. Laboratory experiments attempting to recreate the conditions at Earth's center have revealed something unexpected about how iron behaves at these extreme pressures and temperatures. The crystal structure is not perfectly uniform throughout the inner core, but appears to have a directional quality, what scientists call anisotropy, where seismic waves travel at different speeds depending on which direction they are moving through the iron, faster along the rotation axis from North Pole to South Pole, slower in the equatorial plane, and this directional dependence suggests that the iron crystals are somehow aligned, their lattice directions preferentially oriented in ways that reflect either the conditions under which they formed or the subtle forces acting on them from the rotation of the Earth and the magnetic field generated in the outer core. The exact mechanism of this alignment remains uncertain, part of the ongoing puzzle of understanding the inner core's internal structure, but its existence tells us that even in this most remote and uniform-seeming environment, there is complexity, there is organization at scales beyond the individual crystal, patterns imposed by forces so subtle they would be undetectable at the surface, but which, over millions of years of growth and adjustment, have left their mark in the preferred orientation of countless iron crystals. The atoms in these crystals have been in their current positions for varying lengths of time, depending on when the layer of inner core containing them crystallized, some for nearly 1 billion years if they froze onto the inner core's surface during its earliest growth, others for only a few million years if they solidified more recently, but all of them share the quality of being utterly motionless relative to their neighbors, locked into the lattice with no possibility of diffusion or migration, experiencing time not as a sequence of events, but as a continuous unchanging present, where each moment is identical to the last and the next, where nothing happens because nothing can happen, where existence reduces to the simple fact of occupation of space, atoms being exactly where they are because the pressure gives them no alternative. It is a form of stability so complete it approaches the abstract. Atoms behaving not like matter as we experience it, but like mathematical points in a geometric pattern, present but inactive, real but unchanging, participants in existence but not in process. And if there is such a thing as perfect stillness in a universe where everything is always moving at some scale, then perhaps these iron atoms come as close to achieving it as physical matter can, vibrating in place with thermal energy but going nowhere, surrounded by identical neighbors in every direction, experiencing conditions so extreme and so stable that their state has been locked in for an age measured in tens or hundreds of millions of years and will remain locked until the Earth itself grows cold. The iron at the very center of the inner core, the first iron to crystallize when the inner core began forming, has been solid for longer than anything else in this deepest of all possible locations. And while we cannot know its exact age without better understanding of when the inner core began to form, it is possible that this central iron has been crystalline for a substantial fraction of the planet's history, making it, if not the oldest structure inside the Earth, then certainly among the most perfectly preserved. Because nothing down here ever changes, nothing disturbs the pattern, nothing erodes or oxidizes or breaks down or transforms. The atoms simply remain, held in their crystalline arrangement by forces that have not weakened and will not weaken for billions of years to come. And there is something both comforting and slightly terrifying about this degree of permanence. This absolute resistance to change, because it represents a form of existence so different from anything we experience that it barely seems like existence at all. More like a geometric theorem made physical, a proof of stability written in iron and sustained by the weight of a world. And yet it is real. It is happening right now, kilometers beneath our feet. This profound stillness at the heart of everything. Among all the ancient structures we have encountered on this descent, perhaps the most remarkable are those that have survived not just structurally, but chemically, regions of the deep mantle that have remained isolated from the mixing and recycling processes long enough to preserve the original composition of the material from which Earth accreted. Primitive reservoirs that still carry within their atomic arrangements the chemical signature of the solar nebula, the cloud of gas and dust from which the planets condensed over 4.5 billion years ago. And these reservoirs are remarkable precisely because they should not exist, because the mantle convects and mixes and homogenizes over geological time, because material is constantly being stirred by the slow currents that drive plate tectonics and volcanic activity. And yet isotopic analysis of certain volcanic rocks erupted from deep mantle sources reveals compositions that cannot be explained unless somewhere down there, hidden in the planet's interior, there are pockets of rock that have never been processed through the surface recycling system, that have never been melted and erupted and subducted and melted again, that have simply remained where they were placed during the Earth's formation, chemically pristine after billions of years of planetary evolution. The evidence for these primitive reservoirs comes not from direct samples, because we cannot drill deep enough to reach them, and they do not often participate in volcanism, but from the subtle chemical fingerprints they leave in the magmas that occasionally tap into them, and in particular from the ratios of certain isotopes, atoms of the same element with different numbers of neutrons, that serve as traces of geological processes because they are not affected by chemical reactions or physical transformations, but only by radioactive decay, which proceeds at a fixed rate regardless of temperature or pressure or any other environmental condition. When we analyze volcanic rocks from oceanic islands like Hawaii or Iceland, which are thought to originate from mantle plumes rising from great depth, we sometimes find isotopic ratios that are distinct from those in mid-ocean ridge basalts, which sample the upper mantle. And these distinct ratios can be interpreted as evidence that the magma has mixed with material from a reservoir that has been isolated for a very long time, long enough for certain radioactive parent isotopes to decay into their daughter products at ratios that differ from the well-mixed upper mantle, creating a chemical signature that acts like a timestamp, telling us how long the material has been separated from the rest of the convecting system. One of the most revealing traces comes from noble gases, particularly helium, which exists in two stable isotopes, helium-3 and helium-4, and these two isotopes have very different origins and histories in the Earth. Helium-4 is constantly being produced by the radioactive decay of uranium and thorium in the mantle, accumulating over time at a predictable rate, while helium-3 is largely primordial, present in the solar nebula from which Earth formed, but not produced in significant quantities, by radioactive decay, which means that any reservoir that has been closed off from mixing since the planet's formation should have a relatively high ratio of helium-3 to helium-4 compared to the upper mantle, which has been degassed repeatedly through volcanic activity and has lost much of its primordial helium while accumulating radiogenic helium-4. And indeed, certain volcanic systems do show elevated helium-3 to helium-4 ratios, suggesting that they are tapping into deep reservoirs that have retained at least some of their primordial gas inventory, a whisper from the planet's earliest days preserved in the spaces between atoms, waiting in the dark for billions of years before finally being carried to the surface in a pulse of rising magma. These primitive reservoirs, if they exist in the form suggested by the isotopic evidence, are likely located in the deep lower mantle, perhaps associated with the large, low shear velocity provinces we discussed earlier, the massive anomalous regions detected by seismic imaging beneath Africa and the Pacific, which may represent either accumulations of ancient subducted crust or pockets of primitive mantle that have resisted being mixed into the general convecting system, or perhaps some combination of both, layered and interwoven in ways that seismic waves cannot fully resolve. The key to their survival is their position in the deepest mantle, where convective velocities are lowest and where density stratification may create barriers to mixing, combined with their composition, which may make them slightly denser than the surrounding mantle and thus resistant to being entrained in upwelling plumes, allowing them to remain at depth while the mantle above them circulates and stirs and slowly homogenizes. They are not completely isolated, because nothing in a convecting system is ever completely isolated, but they are isolated enough that their chemical evolution has followed a different path from the rest of the mantle, and that difference, though subtle, is detectable in the volcanic rocks that occasionally sample them, carrying their chemical message to the surface where we can read it if we know how to look. What this means is that there are places inside the Earth where the chemistry has changed very little since the planet's formation, where the ratios of elements and isotopes still reflect the proportions present in the planetesimals that collided and accreted to build Earth. And this is extraordinary because almost everything else about the planet has been transformed, the surface recycled countless times, the crust differentiated and redifferentiated, even the core separated out from the mantle early in Earth's history, taking with it most of the iron and leaving behind a mantle depleted in siderophile elements. And yet, through all these changes, through all the heat and motion and chemical reorganization, these primitive reservoirs have somehow maintained their original character, not because they are protected by any special barrier, but simply because they occupy regions where the stirring is incomplete, where the mixing time is longer than the age of the planet, where isolation is a consequence of geometry and density and the particular pattern of convective flow that has characterized this planet's evolution. They are witnesses not in the sense of having observed anything, but in the sense of preserving within their composition a record of initial conditions, a baseline against which we can measure how much the rest of the mantle has changed, and in doing so they provide a reference point for understanding planetary differentiation, a glimpse of what Earth was like before it became the layered, compositionally complex body we inhabit today. The atoms in these primitive reservoirs have been neighbors for longer than almost any other atoms in the planet, locked together not by bonds, but by the simple fact of proximity in a system where diffusion is too slow to allow them to separate, where they formed a partnership at the moment of planetary accretion and have maintained it through all the subsequent upheavals, a molecular marriage that has lasted billions of years, not through any active commitment, but through passive persistence, through the basic physics of viscous flow at mantle conditions where mixing is incomplete and memory is long. When we attempt to comprehend the age of these structures, to truly grasp what it means for something to have endured for billions of years, we inevitably confront the limits of human temporal intuition, because our experience of time is rooted in the rhythms of days and seasons and lifetimes, durations we can measure against our own existence, and even when we extend our imagination backward through recorded history, through the rise and fall of civilizations, through the entire span of human presence on this planet, we are still operating within a time frame that represents less than 1,000th of 1% of Earth's existence. A flash so brief that if the planet's history were compressed into a single year, all of human civilization from the first cities to the present moment would occupy only the final few seconds before midnight on December 31st, and everything we consider ancient by human standards, the pyramids, the oldest written languages, the earliest cave, paintings, would all cluster within that same final second, indistinguishable from the present at this scale, while the structures we have been contemplating, the zircon crystals and cratonic roots and primitive mantle reservoirs, would have been in place since January or February or March of that same year, already old beyond measure before the first living cell divided, already stable and enduring before there was anything on the planet capable of noticing their existence. The challenge in thinking about deep time is not just the magnitude of the numbers involved, though those are certainly difficult enough, but the fact that geological processes operate according to different rules than the processes that shape our daily experience, unfolding at rates so slow they might as well be motionless from any perspective shorter than millions of years, and yet given sufficient time, these imperceptible rates of change accumulate into transformations so complete they remake entire landscapes, build mountain ranges from flat seabeds, grind those mountains back into sediment, carry continents across the globe, open and close ocean basins, and through it all, the oldest structures remain, not because they are immovable, but because they happen to exist in configurations that have not yet encountered the specific combination of forces necessary to dismantle them. A craton endures not because it is eternal by nature, but because in the time since its formation, nothing has come along capable of destroying it. And while that may seem like a distinction without a difference, it is actually fundamental to understanding geological persistence, because it means these structures are not permanent in any absolute sense, but only in relation to the specific conditions that have prevailed during their existence. And if those conditions were to change, if the Earth were suddenly subjected to impacts or tidal forces or thermal pulses of sufficient magnitude, even the most ancient formations could be obliterated, their billions of years of patient endurance ending in moments. What saves them, what has saved them throughout Earth's history, is not invulnerability, but isolation from catastrophe. The simple fact that the planet is stable enough, gentle enough in its internal processes, that the forces acting on its deep structures rarely exceed the threshold necessary to cause fundamental reorganization. And when such forces do arise, they tend to be localized, affecting specific regions while leaving others untouched, so that even during major events like the assembly or breakup of supercontinents, when entire plates are colliding or rifting apart and volcanism is widespread, there are always quiet zones, stable interior regions far from the action, where the old structures continue their patient existence without interruption. The Earth is catastrophic at human scales, earthquakes and eruptions and landslides that devastate in seconds. But at geological scales, it is surprisingly gentle, its most dramatic transformations playing out so slowly that at any given moment the change is nearly imperceptible. Mountain building that takes millions of years to add a single kilometer of elevation, erosion that requires equally long periods to remove the same amount. And in this gentle rhythm, there is room for persistence, for structures to remain essentially unchanged, while the surface around them cycles through generations of landscapes, each lasting longer than any human mind can properly conceptualize. To grasp what a billion years means requires more than simply adding zeros to numbers we already understand, because a billion is not just a large number, but a fundamentally different category of duration, a span so vast that cause and effect become decoupled in ways that seem almost meaningless, where the connection between what something was and what it has become is so attenuated by the sheer passage of time that it is difficult to maintain any narrative continuity across such intervals. The primitive mantle reservoirs that have been isolated for perhaps 3 or 4 billion years have been separate from the mixing mantle for longer than multicellular life has existed, longer than photosynthesis has been producing oxygen, longer than there have been continents in any form we would recognize. And yet, they are not inert historical artifacts, but active components of the planet's present-day system, participating in mantle convection at rates measured in centimeters per century, influencing the chemistry of volcanic eruptions in ways that betray their ancient origin, existing simultaneously in the deep past through their composition and in the continuous present through their ongoing physical presence. They are not fossils of a former Earth, but surviving pieces of it, still here, still participating, still influencing outcomes. And the fact that they can do this, that they can remain chemically distinct while still being physically integrated into the planet's active systems, reveals something profound about how Earth organizes itself, how it manages to maintain heterogeneity and memory, even while constantly churning and transforming. Perhaps what is most remarkable about these ancient structures is not that they have survived, but that their survival matters, that we can detect them, study them, learn from them, use them to reconstruct conditions and processes that would otherwise be completely lost to us. Because unlike human memory, which degrades with time and becomes unreliable after decades or centuries. Geological memory, when it is preserved, is perfectly faithful, the atoms and isotopes recording their formation, conditions with a precision that does not fade, that cannot be corrupted by forgetting or reinterpretation. That simply is what it is, as accurate now as it was when the record was first written. And in reading that record, in extracting from silent stone the story of a planet's formation and evolution, we participate in a form of communication across time that has no parallel in human experience, learning from structures that have no awareness of what they preserve, receiving messages from ages so remote that the sender and receiver exist in effectively different worlds. And yet the communication succeeds, the information transfers. The past speaks to the present through the endurance of matter. The ancient structures we have been contemplating exist in absolute darkness, in places no human will ever visit, under conditions no instrument could survive, and yet we know about them. We can map their locations and measure their properties and deduce their compositions, not through direct observation, but through the way they disturb the passage of seismic waves, those pulses of mechanical energy that travel through rock whenever an earthquake occurs, propagating outward from the rupture, point in all directions, passing through the entire planet, and eventually arriving at seismometers on the far side of the world, carrying in their travel times and amplitudes and waveforms, a record of everything they encountered along the way, every boundary they crossed, every region of anomalous temperature or composition they passed through. And it is by listening carefully to these waves, by analyzing thousands upon thousands of earthquake recordings from stations distributed across the globe, that seismologists have gradually assembled a picture of Earth's deep interior, a kind of acoustic image constructed from the shadows and echoes that seismic waves create as they navigate through heterogeneous rock. The process is similar in principle to how a medical ultrasound creates an image of structures inside the body, or how bats navigate by echolocation, interpreting reflected sound waves to build a mental map of their surroundings, except that in Earth's case, the sound is not directed intentionally, but emerges spontaneously from the violent slip of tectonic plates, and the receivers are not concentrated in one organism, but scattered across the planet's surface, and the structure being imaged is not a liver or a cave, but the entire interior volume of a planet, which means the computational challenge of transforming the raw seismic data into a coherent picture is immense, requiring sophisticated mathematical techniques and enormous computing power to solve what is essentially an inverse problem, working backward from the observed wave arrivals to infer the three-dimensional distribution of seismic velocities that would best explain those observations. Seismic waves come in several varieties, but the two most important for imaging Earth's deep interior are P waves, which are compressional waves that travel through both solid and liquid by alternately squeezing and stretching the material they pass through, and S waves, which are shear waves that travel only through solids by moving material side to side, perpendicular to their direction of propagation. And the fact that S waves cannot propagate through liquid is how we know the outer core is molten, because S waves generated on one side of the planet simply disappear when they try to enter the outer core, creating a shadow zone on the opposite side where no direct S waves arrive, while P waves continue through, but are slowed and bent by the low velocity of the liquid ion, arriving later than they would if the core were solid. These basic observations, made in the early 20th century, established the fundamental layered structure of the planet, the existence of crust, mantle, outer core, and inner core. But modern seismic imaging goes far beyond this, looking for subtle variations in wave speed within each layer, anomalies that might be only a few % faster or slower than the surrounding rock, but which, when mapped across the entire mantle, reveal structures like subducted slabs and mantle plumes, and the large low-velocity provinces at the base of the mantle that we have discussed as possible locations for primitive reservoirs. The way seismic velocity varies with rock properties is reasonably well understood from laboratory experiments and theoretical calculations, and in general, waves travel faster through cold, dense, crystalline material and slower through hot, partially molten, or compositionally light material. which means that a faster than average region in the mantle likely indicates either a cold slab of subducted oceanic lithosphere or a compositionally dense accumulation, while a slower than average region might indicate a hot mantle plume or a pocket of material with different chemistry. And by carefully analyzing these velocity anomalies and comparing them with what we know about how different materials behave at mantle conditions, seismologists can begin to distinguish between thermal and compositional effects, to say not just that something is different, but what kind of different it is, whether we are seeing temperature variations or density variations or both. And this level of interpretation is what allows us to make statements about the existence of primitive reservoirs or the presence of ancient subducted crust, because these structures have distinctive seismic signatures that can be recognized once you know what to look for. Patterns of velocity variation that match what we would expect from material that has been isolated for billions of years, or from basaltic crust that has been transformed into high-pressure mineral assemblages. But seismic imaging has limits, and these limits are important to acknowledge because they remind us that our picture of Earth's deep interior, while scientifically grounded and constantly improving, is still fundamentally an inference, a best interpretation of indirect evidence rather than direct observation. And there are aspects of the deep Earth that seismic waves simply cannot resolve, either because the features are too small to affect wave propagation in detectable ways, or because different types of anomalies produce similar seismic signatures that cannot be distinguished with current data. The resolution of seismic imaging degrades with depth, becoming coarser in the lower mantle where we have fewer rays crossing through any given volume. And this means that while we can detect the existence of large-scale structures like the African and Pacific low-velocity provinces, we cannot say with certainty what their internal structure looks like, whether they are homogeneous or layered, sharp-edged, or diffuse, because the seismic data does not contain information at that scale, and any attempt to image finer details risks creating artifacts, apparent structures that are actually just mathematical noise introduced by the imaging process itself. And yet, despite these limitations, despite the inherent ambiguity of working with indirect evidence, seismic imaging remains our best tool for exploring the inaccessible interior, our only way of seeing into the planet beyond the few kilometers that drilling can reach, and the fact that it works at all, that we can extract meaningful information about structures thousands of kilometers deep from the timing and amplitude of waves recorded at the surface, is itself remarkable, a testament to both the regularity of wave propagation through rock and the sophistication of the mathematical techniques we have developed to interpret that propagation. What emerges from this listening, from this patient accumulation of earthquake data and careful analysis of wave behavior, is not a complete or perfect picture, but a functional map, good enough to identify major structures, to track the descent of slabs, to locate regions of anomalous composition, to confirm that the ancient structures we infer from other evidence, from geochemistry and from theoretical modeling, actually exist in the places and with the properties we predict. And this convergence of different lines of evidence, seismic and chemical and theoretical, all pointing toward the same conclusions, is what gives us confidence that we are not merely constructing elaborate fictions, but actually learning something true about the planet's hidden architecture, about the enduring structures that have shaped its evolution and continue to influence its present-day behavior in ways both subtle and profound. There is a paradox at the heart of these ancient structures, a tension between their persistence and the restless dynamism of the planet they inhabit, because Earth is not a static body, but an active one, its interior in constant motion, its surface constantly being remade, heat flowing outward from the core in massive convective cells that drive plate tectonics and volcanism and all the other processes that make this a living planet rather than a dead sphere of cold rock like the moon. And yet, within all this motion, within this continuous transformation, there exist these pockets of profound stability, regions that have remained essentially unchanged for billions of years, not because they are somehow outside the system, but because they are positioned within it in such a way that the motion flows around them rather than through them, like rocks in a river that remain fixed while water streams past. or like the eye of a hurricane, where the air is calm, even as winds rage in the surrounding wall. And this coexistence of change and permanence, of flux and stability, is not a contradiction, but rather a natural consequence of how complex systems organize themselves when given enough time and space to find equilibria. The Earth is both moving and stable, both transforming and enduring, both dynamic and static, and these qualities do not cancel each other out but rather exist simultaneously at different scales and in different domains, creating a layered reality where what is true at one timescale or one location may not be true at another, and learning to hold both perspectives in mind at once, to see the planet as both restless and patient, is perhaps the most important shift in understanding that comes from contemplating geological time. The key to understanding this paradox lies in recognizing that motion and stability are not opposing states, but exist on a spectrum, and where any given structure falls on that spectrum depends on the frame of reference you choose, the timescale and spatial scale at which you are observing. From the perspective of a human lifetime, even the fastest geological processes appear frozen. A continent drifts a few centimeters per year, but in a single human span moves only a few meters, imperceptible unless measured with instruments, and a mountain that is actively rising appears perfectly still, because the rate of uplift is measured in millimeters per year, invisible against the background of seasonal snow accumulation and erosion. But extend the timescale to millions of years, and suddenly the continent has crossed thousands of kilometers. The mountain has risen from sea level to tower above the clouds, and what seemed permanent reveals itself to be transient, a temporary configuration that will inevitably give way to something else. The ancient structures we have been discussing occupy the opposite end of this spectrum, places where even when observed across billions of years the change is minimal, where the motion that dominates elsewhere has been dampened or excluded, where the system has found configurations stable enough to resist being drawn into the general circulation. And these structures persist, not because they are outside of time, but because they exist in domains where the rate of change is slower than the duration we are considering, where a billion years is not long enough for the processes acting on them to accomplish any significant transformation. This creates a landscape, if we can call it that, of differential motion, where some parts of the Earth are cycling rapidly through states while others move glacially or barely move at all. And the boundary between these regions is not sharp, but gradual, a continuum of velocities that ranges from the swift convection of the upper mantle, turning over every 100 million years or so, down through the sluggish stirring of the lower mantle, taking perhaps a billion years to complete a circulation, and finally to the near stillness of the inner core and the isolated primitive reservoirs where motion has effectively ceased from any perspective we can meaningfully apply. Each layer and region moves at its own pace according to its own driving forces and resistances. And while these different regions are coupled to each other through gravity and through the transmission of stresses across boundaries, they are not locked in step, not moving as a single rigid unit, but rather slipping past each other, flowing around each other, existing in a kind of mechanical harmony where each component follows its own trajectory while still participating in the larger system. And it is this decoupling, this ability of different parts to move independently, that allows both rapid transformation and long-term stability to coexist within the same planet. The cratons, for instance, move with the plates they are embedded in, drifting across the surface at centimeters per year as the convecting mantle beneath them drags them along. But while their position changes, their internal structure does not, the thick, cold root that defines them remaining intact, even as it is carried around the globe. And this distinction between external motion and internal stability is crucial to understanding how something can be both moving and unchanging, simultaneously participating in plate tectonics while maintaining its ancient character. The subducted slabs are sinking through the mantle in slow motion, descending at rates that seem impossibly slow by human standards, but which accumulate over millions of years into journeys of thousands of kilometers. And yet, even as they sink, even as they are heated and compressed and transformed mineralogically, they retain a chemical and structural identity that marks them as former ocean floor, distinct from the mantle through which they fall, moving but not mixing, changing but not dissolving, existing in a state between solid and fluid where both qualities are partially true and neither is complete. And the primitive mantle reservoirs, if they exist as we believe, are perhaps the most paradoxical of all, resting in the deep mantle where everything should be convecting and mixing, and yet somehow remaining isolated, neither rising with hot plumes nor sinking with cold slabs, finding some density or viscosity or geometric configuration that allows them to stay put, while the rest of the mantle circulates around them, stable not because they are anchored to anything, but because the forces acting on them happen to balance in a way that produces no net motion, at least not on timescales shorter than the age of the planet. What this tells us is that stability is not the absence of forces, but rather an equilibrium of forces, not a lack of motion, but a balance of motions that cancel, not a withdrawal from the dynamic system, but a particular positioning within it, where the net effect of all the pushing and pulling and heating and cooling happens to be stasis. And this equilibrium is often delicate, maintained by specific conditions that could change if the planet's thermal state or convective pattern were to shift, which means that the ancient structures, while stable for billions of years, are not guaranteed to remain so indefinitely, their persistence contingent on the continuation of the conditions that have protected them. And if those conditions were to change, if some event were to disturb the equilibrium, the structures could be mobilized and recycled despite their great age, joining the general circulation they have so far avoided, their billions of years of isolation ending not gradually, but relatively suddenly as the forces that kept them in place finally yield to forces pushing them elsewhere. If we think about what these ancient structures have witnessed, not in any literal sense because rock does not see or remember in the way living things do, but rather in the sense of what has occurred in their vicinity, what transformations they have remained present through, the sheer scope of planetary history that has unfolded while they sat unchanging in their positions, we begin to appreciate that their persistence makes them not just survivors, but inadvertent witnesses to nearly the entire story of Earth as a habitable world, present before the first oceans condensed, present through the origin of life and its subsequent evolution through countless forms, present through mass extinctions and continental reorganizations and climate shifts so profound they transformed the planet from a snowball encased in ice to a greenhouse with palm trees in the Arctic. And through all of this, through every upheaval and transformation that has defined Earth's history, these structures remained essentially as they were, neither participating in the changes nor affected by them, existing in a state of removal so complete that the entire drama of surface evolution might as well have been happening on a different planet for all the impact it had on a zircon crystal buried in ancient rock, or a pocket of primitive mantle resting 2,000 kilometers below the seafloor. The earliest zircon crystals, the ones that formed over 4 billion years ago when Earth was barely cooled from its formation, existed before there was any substantial atmosphere, before there were continents in the modern sense, possibly before the Moon had fully settled into its current orbit after the giant impact that created it. And these crystals were already ancient by the time the first single-celled organisms appeared, already older than most rocks would ever become by the time photosynthesis began producing oxygen, already veterans of billions of years by the time complex life emerged from the oceans and began the long process of colonizing land. And yet they remain unchanged at the molecular level, their crystal structure identical to the moment they formed, indifferent to the fact that the planet around them has been completely remade multiple times over, that the atmosphere they formed under has been replaced by a chemically different one, that the temperature, regime, and the hydrological cycle and the distribution of land masses have all transformed in ways that would make early Earth unrecognizable to anyone who knew only the modern planet. They have been present through it all, passive observers in the most literal sense, recording nothing except their own formation, preserving no information about subsequent events, and yet their mere existence across such spans gives them a kind of authority, a gravitational weight in our consideration of deep time, because they represent continuity across intervals that dwarf any other form of persistence we know. The cratonic roots have witnessed the assembly and breakup of multiple supercontinents, those periodic gatherings of all the world's landmasses into single enormous continental blocks that occur roughly every 500 million years, driven by the patient workings of mantle convection, which eventually organizes itself into large-scale patterns that pull all the continents together, hold them in proximity for 100 million years or so, and then tear them apart again, scattering the fragments across the globe until the next cycle begins. And through each of these cycles, the cratons have remained intact, participating in the collisions and rifting events, but never being fundamentally altered by them. Their margins deformed perhaps, their surfaces buried under sediments or thrust sheets from neighboring continents, but their deep roots untouched, still cold, still thick, still stable, outlasting every mountain range that formed on their surfaces, every ocean that opened. Between them and their neighbors, every climate regime that prevailed during their long journey across latitudes from equator to pole and back again. They have been tropical and polar and temperate, have been submerged beneath shallow seas and exposed as high plateaus, have supported swamps and deserts and ice sheets, and none of it has mattered to the ancient rock at their core, which continues its existence independent of whatever surface conditions happen to prevail at any given moment. The primitive mantle reservoirs, if they have indeed remained isolated for 3 or 4 billion years, as the isotopic evidence suggests, have existed in their deep positions since a time when the Earth's heat flow was much higher than today, when volcanic activity was more intense and widespread, when the style of plate tectonics, if it even operated in a form we would recognize, was likely quite different from the modern pattern, and they have remained in place through all the subsequent changes in the planet's thermal state and convective organization, through the gradual cooling that has slowed the pace of geological activity, through the oxygenation of the atmosphere which fundamentally altered the chemistry of surface weathering and the nature of sediments being subducted, through the evolution of continents from small scattered blocks to large stable platforms, and their chemical isolation from all these changes means they preserve within their composition a record of what the mantle was like before any of this occurred, a baseline condition that has disappeared everywhere else through mixing and processing and differentiation, surviving only in these protected pockets where the stirring never quite reached, where the isolation has been maintained not through any active defense, but through the simple geometry of convective flow that happened to circulate around rather than through them. What strikes me about this witnessing, this passive presence through unimaginable spans of planetary history, is how completely one-directional it is, because while these structures have been present through all these changes, the changes have not been present to them, have not registered in any way that affects their state or composition, and this asymmetry reveals something fundamental about the relationship between surface and interior, between the thin shell where biology and climate and erosion operate, and the deep interior, where only physics and chemistry at extreme conditions matter. And the two realms, while connected through volcanism and subduction, and the heat flow that drives everything, exist at such different timescales and under such different conditions that they might as well be separate worlds, events of catastrophic significance at the surface, producing no detectable effect in the deep interior, and events of profound importance in the deep interior, the slow rearrangement of mantle convection patterns or the growth of the inner core, having no immediate surface expression, affecting the world above only indirectly and only after delays measured in millions of years. The ancient structures exist in this deep realm, participating in its slow physics, isolated from the rapid changes that define the surface, and their persistence is possible precisely because they are removed from the domain where change happens quickly, where weathering and erosion and biological activity and climate operate on timescales short enough that transformation is continuous and nothing lasts very long without being altered or destroyed or incorporated into something else. To place ourselves in relation to these ancient structures requires a recalibration not just of our sense of time, but of our sense of significance, because we are accustomed to thinking of human affairs as important, our civilizations and achievements and struggles as worthy of attention and memory. And they are, within the context of human history, they matter enormously. But when set against the span, represented by a zircon crystal that has existed for 4 billion years, or a cratonic root that has been stable for 3 billion, the entire human story becomes so compressed, so vanishingly brief, that it occupies a span indistinguishable from zero at the scale these structures inhabit. And this is not a cause for despair or nihilism, but rather an invitation to a different kind of perspective, one where our concerns and achievements neither disappear nor dominate, but rather take their place in a much larger context, part of a planet's ongoing story, but not the center of it. Significant within our own timescale, but invisible at the timescale of the deep Earth. And learning to hold both of these truths simultaneously, to honor human experience while acknowledging its brevity against geological duration, is perhaps one of the more difficult cognitive tasks we face when confronting deep time, because our intuitions want to make it a competition, want to decide whether human time or geological time is more real or more important, when actually they are both real, both important, just operating at such different scales that comparison becomes almost meaningless. The oldest written records we possess go back perhaps 5,000 years, and if we extend our reach to include cave paintings and carved figurines and other evidence of symbolic thought, we might stretch back 40 or 50,000 years. And these feel like immense spans to us because they represent hundreds of human generations. Enough time for languages to evolve and die, for entire civilizations to rise from nothing and collapse into ruins, for technologies to be invented and forgotten, and reinvented. And within the frame of human experience, this is deep time. This is as far back as our cultural memory extends, but placed against the existence of a cratonic root that has been stable for 3 billion years. These 50,000 years of human symbolic culture represent 1/60,000th of the craton's duration, a ratio so extreme it defies comprehension, like comparing a single second to a period of nearly 17 hours, except even this fails to capture the scale. Because we can imagine 17 hours, we have experienced durations of that length, whereas we have no experiential framework for grasping what 3 billion years feels like, no way to internalize it except through these inadequate mathematical analogies that give us numbers but not understanding. And this is before we even consider that Homo sapiens as a species has existed for only about 300,000 years, which sounds substantial until we realize that this is 1/10,000th of the craton's age, meaning that if we compress the craton's entire existence into a single year, our species would have appeared only in the final 50 minutes before midnight on December 31st, and all of recorded history would occupy roughly the last minute of that year. What this means is that from the perspective of the ancient structures, if they had any perspective, which of course they do not, human presence on Earth is a recent development, so recent as to be essentially instantaneous. And not just human presence, but all of complex life, all of animal evolution from the first worms to the present day, all of it contained within the last 10 or 15% of the oldest structure's existence, a late addition to a planet that had already been running for billions of years before anything with a nervous system appeared. And this is not to diminish the significance of life or consciousness, or any of the qualities that make biological existence remarkable, but simply to note that the Earth was doing interesting things for a very long time before biology entered the picture, was differentiating and convecting and building continents and cycling materials through its interior in complex patterns that required no living thing to make them happen, no observer to give them meaning, and that activity continues largely independent of whether there is anyone or anything paying attention to it. The ancient structures neither knowing nor caring that they have been joined on the planet's surface by creatures capable of noticing their existence and wondering about their age, because the physics that governs their behavior does not require awareness or intention or any quality we might associate with agency. It simply unfolds according to the laws that govern matter under these conditions, and the fact that some of that matter has organized itself into forms capable of studying the rest is extraordinary, but not, from the planet's perspective, necessary. The humility that comes from this recognition is not the humility of insignificance, not a diminishment of human value or experience, but rather the humility of perspective, the understanding that we are part of something much larger and longer lasting than ourselves, that the ground beneath our feet has a history that preceded us by an almost unimaginable margin and will continue after us for equally long spans, that our moment of existence, however rich and complex and meaningful it feels, from inside is, from the planet's perspective, a brief flicker, and yet that flicker is still real, still contains everything that matters to us, all the love and suffering and creativity and struggle that constitutes human life, none of which is diminished by being brief any more than a beautiful sunset is less beautiful because it lasts only minutes, or a piece of music is less moving because it ends. Duration and significance are not the same thing, and one of the errors we make when confronting deep time is assuming that because geological processes operate over billions of years, they must be more important than human processes that operate over decades, when actually importance is not a property of time, but a property of perspective. And from a human perspective, human timescales are exactly the right timescales to care about. The fact that they represent an infinitesimal fraction of planetary history being interesting but not relevant to how we should live or what we should value within our own brief existence. And yet there is something calming about knowing that beneath all the urgency and change that characterizes human time, beneath the news cycles and political upheavals and technological transformations that make it feel like everything is always in flux, always accelerating, always on the verge of some critical transition, there exists this foundation of patient stone that has been here for billions of years and will remain for billions more, indifferent to our crises and triumphs alike. Neither judging nor responding, but simply being, holding its position in the dark, and perhaps what these ancient structures offer us, beyond their scientific value, as records of planetary history, is a kind of emotional anchor, a reminder that not everything changes at the pace of human affairs, that there are domains of existence where stability is measured in billions of years rather than election cycles or product releases or social media trends, and that this stability is not opposed to our brief energetic existence, but rather provides the platform on which it occurs, the stage on which the drama unfolds. When we walk across the surface of the earth, when we feel solid ground beneath our feet and trust that it will hold our weight, we are participating without knowing it in a relationship with these ancient structures, because the stability we rely on, the firmness that allows us to build homes and plant crops and construct roads and simply stand upright without thinking about it, is ultimately provided by the cratonic roots and the lithospheric plates that rest on them, structures that have been performing this service of holding the surface in place for billions of years before we arrived, and will continue doing so long after we are gone. And yet we go about our daily lives almost entirely unaware of this dependency, treating the ground as simple backdrop rather than as an active participant in our existence, something that is there because it has always been there and always will be, which from a human timescale perspective is essentially true, even though from a geological perspective the surface is constantly changing, constantly being remade, constantly moving and transforming in ways that would be obvious if we could watch at the appropriate speed. The disconnect between how we experience the Earth and what the Earth actually is, between the static solid ground we think we stand on and the dynamic flowing system that exists beneath our feet, is total. And this is probably necessary for psychological health, because if we were constantly aware of the fact that the continents are drifting, that the mantle is convecting beneath us, that everything we consider permanent is actually temporary when viewed at geological scales, we would find it difficult to maintain the sense of stability and continuity that human life requires. And so we have evolved, both biologically and culturally, to perceive the world at human timescales, to filter out the changes that happen too slowly to affect us, and to treat as permanent anything that persists longer than a few human generations. But there is something to be gained from occasionally stepping outside this comfortable perception, from allowing ourselves to become aware, even if only briefly and intellectually rather than experientially, of the deep time and ancient structures that underlie our everyday existence. because this awareness can provide a kind of perspective that is difficult to achieve through other means, a way of contextualizing our concerns and anxieties and preoccupations that neither trivializes them nor allows them to consume our entire field of view, placing them instead in a larger frame where they remain important within human context, but lose some of their absolute urgency when considered against the patient endurance of geological time. This is not about escaping human concerns by fleeing into contemplation of deep time, not about using the vastness of geological history as an excuse to avoid engaging with the problems and responsibilities of the present moment, but rather about developing a kind of dual vision where we can attend to immediate needs and long-term patterns simultaneously, where we can care deeply about human-scale events, while also holding a quiet awareness of the much larger context in which they occur. And this balance, when achieved, can produce a particular quality of calm, a sense of proportion that keeps anxiety from spiraling into panic, that allows us to take things seriously without taking them so seriously that we lose our ability to think clearly or act effectively. The ancient structures, in this sense, offer us more than just scientific knowledge or philosophical material for contemplation. They offer us a kind of practical wisdom about how to exist in time, how to understand ourselves as both momentary and part of something continuous, how to be fully present in our brief span, while also recognizing that this span is embedded in a much longer duration that preceded us and will follow us. And there is something stabilizing about this recognition, something that settles the mind in a way that purely human-focused thought often cannot. Because when we are trapped entirely within human timescales, when our entire frame of reference consists of days and months and years and decades, we can become overwhelmed by the pace of change, by the sense that everything is always urgent, always critical, always demanding immediate response, and we lose access to the calmer rhythms that govern longer cycles, the seasonal and generational and geological, patterns that remind us that not everything happens at once, that some processes require patience, that there is value in slow unfolding as well as rapid action. The ancient structures embody this slower rhythm, existing in a state where change is so gradual it approaches stasis. And while we cannot and should not try to live at their pace, because human life requires engagement with events that unfold over hours and days, not millions of years, we can draw something from their example, a reminder that not all stability comes from rigidity, that endurance can be a form of flexibility rather than resistance, that lasting through time often means finding an equilibrium with the forces around you rather than trying to stand against them. The cratons persist, not because they are harder than other rock, but because they are thick and cold and positioned in ways that allow the forces of plate tectonics to flow around them rather than through them. And there is perhaps a lesson here about how to maintain stability in a changing environment, not through absolute rigidity that eventually breaks under stress, but through a kind of responsive equilibrium that accommodates change in some dimensions while preserving core identity in others. And while the comparison between geological structures and human life should not be pushed too far, because they operate under completely different rules and constraints, there is still something to be learned from observing how the planet itself manages the tension between stability and change, how it maintains continuity across billions of years, not by preventing all transformation, but by organizing itself so that some regions can remain stable while others do the necessary work of adaptation and renewal. We live on a planet that is simultaneously ancient and young, permanent and temporary, unchanging and constantly transforming, and our own lives partake of this same paradox, being both brief moments and complete experiences, both insignificant flickers and the totality of what matters, and learning to hold this paradox without trying to resolve it in either direction, without fleeing into either pure presentism that denies continuity or pure eternalism that denies change, is perhaps one of the ways we can use our knowledge of deep time, not just as abstract information, but as a tool for living more thoughtfully and calmly in the present. The ancient structures will be here tomorrow and the day after that and a million years from now, largely unchanged, continuing their patient existence whether we think about them or not. And there is something oddly comforting about this, about knowing that our individual choices and mistakes and achievements, however significant they feel in the moment, and however much they matter within human context, do not threaten or enhance the fundamental stability of the planet, that the ground will continue being ground regardless of what we do on its surface, that the deep structures that have persisted for billions of years are not dependent on us for their continuation. And this is comforting not because it makes our actions meaningless, but because it relieves us of the burden of cosmic responsibility, allows us to care about human-scale problems without feeling like the entire universe depends on us getting everything exactly right. Perhaps the most profound thing about these ancient structures is not what we can know about them, but what must remain unknown. Because despite all our scientific tools and theoretical models and careful analysis of seismic data and isotopic ratios, we are still fundamentally limited in our ability to comprehend what it means for something to have existed for billions of years, to have remained essentially unchanged while everything around it transformed repeatedly, to have been present through spans of time so vast that our largest units of measurement become inadequate, our metaphors break down, our imagination fails to construct any meaningful representation of the duration involved. We can calculate the age of a zircon crystal with remarkable precision, can tell you that it formed 4.4 billion years ago, give or take a few million years, can describe the chemical environment of its crystallization and the subsequent history recorded in its internal structure. But all of this knowledge, accurate as it is, still does not convey what it feels like, if feeling is even the right word, for those atoms to have been arranged in that particular lattice for that incomprehensible span. And perhaps this failure of comprehension is not a bug, but a feature, not a limitation to be overcome, but a boundary to be respected. Because some things exist at scales so far removed from human experience that trying to fully grasp them is like trying to hold water in your hands. The harder you squeeze, the more it escapes. And maybe the appropriate response is not to squeeze harder, but to simply acknowledge the gap between what we can measure and what we can truly understand. The structures themselves offer no guidance on this question, no wisdom to impart about their own endurance, because they are not conscious and never have been. They do not know they are ancient any more than a newborn crystal knows it is young. They simply exist in whatever state the physical conditions around them dictate, responding to pressure and temperature according to the laws of thermodynamics and nothing more. And yet we cannot help but project onto them some quality of witness or memory or significance that they do not actually possess, cannot help but feel that their age gives them weight beyond their mere physical mass. And this projection is perhaps more about us than about them, about our need to find meaning in duration, to believe that time passing leaves some mark beyond the purely mechanical effects of erosion and deformation, to imagine that existence across such spans must mean something even if we cannot articulate what that meaning might be. And perhaps this is acceptable. Perhaps the meaning we find in these structures does not need to reside in the structures themselves, but can emerge from our encounter with them, from the way their existence challenges our assumptions about permanence and change, from the perspective shift that occurs when we allow ourselves to really sit with the idea that there are things much older than us, continuing to exist quietly beneath our feet, indifferent to our presence, but somehow making that presence possible by providing the stable foundation on which the brief drama of biological existence unfolds. We began this journey in the stillness of night, sensing the weight of ancient stone beneath us, and having descended through layers of increasing depth and age, having encountered crystals that predate continents and continental roots that have outlasted supercontinents and reservoirs of primordial rock that remember the planet's formation. We return now to that same surface, that same night, but perhaps carrying with us a slightly different sense of what the ground beneath us represents. Not just solid matter, but an archive of deep time. Not just a platform to stand on, but a participant in a story that began billions of years before we arrived and will continue billions of years after we depart. And knowing this changes nothing and everything simultaneously, leaves the ground exactly as solid as it ever was, but adds to that solidity a dimension of temporal depth that was always there, but perhaps not always noticed. And in noticing it, we become, however briefly, participants in a kind of attention that spans scales, that connects the immediate sensation of earth beneath feet to the almost unimaginable spans of geological endurance. And in that connection, there is something like peace, something like understanding, even if the understanding is incomplete and the peace is temporary, because both are real within their own context, both matter within the frame of human experience, and that is enough. The ancient structures will continue their patient existence long after this particular night has passed, long after every night we will ever experience has passed, and they ask nothing from us, require no acknowledgement or appreciation, their persistence entirely independent of whether anyone notices or cares. And yet here we are, noticing, caring, spending these quiet hours in contemplation of stone and time and the strange fact of duration. And if this act of attention seems insignificant against the vast indifference of geological time, perhaps that is precisely what makes it valuable. The fact that it is freely chosen, undertaken, not because it is necessary, but because something in us wants to understand, wants to connect, wants to place ourselves in relation to these ancient witnesses, even knowing that the relationship is entirely one-sided, that we are changed by the encounter, but the structures remain exactly as they were, unmoved and unmoving, resting in their deep positions, holding their secrets, not deliberately but inevitably, simply being what they are. And sometimes, that is all we can ask of the world, that it be what it is, that it continue its patient work regardless of whether we understand it, and that we, in turn, can observe that work with whatever combination of science and wonder we can muster, seeking neither to possess nor to solve, but simply to be present to the mystery of duration, the fact of ancient stone, the quiet endurance of structures that have outlasted everything we might imagine, and will continue their existence long past the horizon of anything we can predict. If this journey brought you a sense of calm, you can subscribe to Quiet Science and continue exploring these silent depths with us.